Cool. All right. So, as was sort of mentioned, I'm a second-year student at Abertay. This year, I was helping out with the Ethical Hacking Society as a secretary, and I was also one of the organizers for this year's Security conference. This summer, I'll be joining the wonderful folks at Skyscanner as an intern, and I'm generally interested in the idea of user experience versus security, embedded devices, payment technologies, and public transportation. So the reason why I think everyone might find this topic interesting is because most web apps implement some form of authentication system, because it's important for websites to know who you are. And login forms come in all sorts of shapes and sizes. So you might have very simple, like bootstrap type login form. You might have something a bit more complicated, with a forgot password field, with a sign-in field. Or you might have all sorts of different options for how you can log in, different kinds of usernames, log in with an email, whatever. But not all login forms are equally secure. So what do I mean when I say a login form is secure? And there's the obvious sort of definition of, your login form is using HTTPS. And definitely now this is something that should be considered, a bare minimum requirement. As of January, Chrome will show a not secure warning if you go to a website that has a password field that isn't being served over HTTPS. And Firefox will even display a little banner saying this connection is not secure on the password field, which has led to a few people being angry, but it's still something that we're definitely not going to turn back on. HTTPS is something that's a necessity now in 2017. But HTTPS only secures the transport layer. So it protects information while you're communicating with the server, but it does not protect data at rest. And as it turns out, we're really bad at protecting data at rest. Services are breached almost every other day. There are password dumps that are leaked, all the time. And further, we're also really bad at making sure that information that's stolen from one service can't be reused on another service. And here's an example of, Mark Zuckerberg, who had his password for multiple social networks stolen because he used the same password on multiple services. And really, this is a problem with static information because it can be stolen from one service, from one organization, and it can then be reused across multiple organizations. And this is why static information on its own is absolutely terrible for authentication. So this is why a lot of web services try to implement two-factor authentication as a sort of attempt to solve this problem. So two-factor authentication combines something that you know with something that you have. Essentially, you keep the password, but you also add a physical layer to it. Now, as companies first started implementing two-factor authentication, some people missed that, that static information is bad slide. So a lot of banks, particularly in South America, some in Spain, implemented these code cards. Effectively, they'd be printed perhaps on the back of your debit card, would be given to you when you signed up for online banking. And whenever you logged in or you were trying to do some sort of sensitive action, it would ask you to enter a code from the grid. So, this is fine because a different code is requested each time you do something. So you can't just look at one request and, reuse the same code again, unless you can capture, 20, 30 login attempts, and then you've probably captured all the codes on the card. But, still one code doesn't reveal the remaining codes on the card. But, man in the middling the user is really hard. Usually requires some sort of malware, or you have to have physical access to the user's network. It's so much easier to phish a user. You can just tell a user, we need to reactivate your card, otherwise you'll lose access to online banking. And you can just ask them for all the codes on their card. And this is straight up a real phishing website for a bank in Venezuela that hit several people who just went, okay, I have to reactivate my card. Let me enter all of the numbers. So static data in a physical format is still static data. It's bad. It's still something that can be stolen. In this case, it's not something that can be reused across multiple services, but it's still something where the user can be compromised and they won't necessarily know because you don't need to physically steal the card in order to steal the codes from it. So, okay, how can we then quickly provide a user with a one-time use code? Something that we can generate on the fly, something that can't be stolen from them. Users have phones. We can text them one-time use codes. And a lot of services do this. So here's an example from PayPal sending me a confirmation code because I haven't signed into my PayPal account on that computer before. And the problem with this is authentication, either by text messages or through phone calls, doesn't prove that you have possession of that phone. Rather, it proves possession of that phone number. And unfortunately, a lot of cell phone carriers aren't taking reasonable measures to ensure that your phone number doesn't fall into the wrong hands. So here's a news article describing an activist who had someone go to his telco and pretend to be him and have his SIM card reissued. And at this point, the person stole his phone number, was able to break into his Twitter account and impersonate him. Additionally, signaling system 7, which is what's used as a sort of base for all global telecommunications, allows your phone number to be hijacked without your carrier's cooperation. Essentially, you can pretend to be roaming as a user or signal to other phone networks that you'd like SMSs to be rerouted to your network, and you can take that over, although that involves you working for a telco and is a bit more, nation-state level. But these sorts of attacks, do happen. They happen. Signaling System 7 attacks specifically happened in Iran, where the state was trying to take over some activists' Telegram accounts. Additionally, SMS verification or call verification causes problems when the user's roaming or they're out with service areas. So I had a lot of issues trying to access my PayPal account while I'm visiting my family in the Dominican Republic because I don't want to roam there. It's very expensive. And, I can't receive the SMS, but I'd still like to prove, who I am. So, okay, can we provide some sort of, some starting point when the user signs up from which they can generate codes independently without having to go online, something that can't easily be cloned. We could give the user a code generator. And these things have been around, for quite a while. RSA keys are really common in banks. Some people are, use them internally within organizations as a form of two-factor authentication. But the basic idea is that both the website and the device have a shared secret key. And a lot of these work on the TOTP protocol. And the way that works is that you compute the HMAC of the current time using the shared secret key. And as long as the key isn't intercepted during the initial setup, the key can't be externally determined. So if your bank hands you a fob that they programmed internally, then that programming can't be externally intercepted. But fobs can be expensive, they can be really inconvenient, they're kind of bulky, you have to change the batteries out in them every now and then. So instead, a lot of companies use apps that generate authentication codes for you. So here are a couple popular examples. There's Google Authenticator, SteamGuard, and the Battle.net Authenticator. And it's a similar idea. When you go to sign in to a service, your app gives you a code which you then enter onto your computer. And a lot of these are based on the time-based one-time password algorithm. And basically, the app, or the fob, and the service agree on 5 parameters. You agree on a secret key, what the current time is, an interval, a hash function, and a token length. Usually the interval is 30 seconds. Usually your hash function will be SHA-1, and usually your token length is about 6 characters. So, for example, let's say that this is our key, and it's currently, about 24 hours ago yesterday. And we'll use a 30-second interval, SHA-1 and 6-digit tokens. So this TOTP starts off by calculating how many seconds have gone by since January 1st, 1970, and so you get this Unix timestamp. You divide that timestamp by your interval, you get this other lovely number. Then you calculate the HMAC of that number with your secret key, and you get this long hash. You take the 4 least significant bits from the hash, in this case this would be E, and you use it as an offset in the original hash. So you just count, 14 characters up and grab everything from 14 characters on. You convert that to binary, and you take 4 bytes starting from the offset and discard the most significant bit. So then you get this number, and the token is the lowest 6 digits, and if necessary, you pad that on with zeros. If the code generated matches on both sides, everything's great, right? So this is also pretty simple math. There are a bunch of libraries to do this. There are all sorts of websites that implement this. It's pretty common for TOTP to be used for second factor authentication. But there's a problem, right? Because, as I mentioned, the key fobs, they're really inconvenient. It's the same thing with software tokens. Maybe you're using some sort of enterprise grade system. You don't want to have to share these tokens around. You don't want to have to deal with provisioning them. And so a lot of people, they simply take a webcam and they point it at all of their tokens, and they stream these on the internet. So when you go to sign in to this, secure service, you pull up the webcam feed and you look for the fob that you're being asked for, and you zoom in, you read the code off it, and then you type that in to your web service. And that's kind of terrible. You really shouldn't be doing that, because it gets rid of this whole idea of requiring that you have physical access to the key fob. And there are all sorts of webcam feeds like this if you just look around on Showdown. You can avoid this by requiring user interaction, right? So if you have a fob or a software token that requires that you press a button, you use as a counter, something like that, then you avoid someone being able to just point a webcam at it, right? So there's HOTP, which is exactly the same as TOTP. It just uses a counter instead of the current time. But the problem is that if you have a toddler or someone that just sort of presses this button over and over and over again, then the state of the token will be different from the state on the server. The counters will be way out of sync. So there's sort of some practicality issues with having a counter-based system. So instead, you have some apps that take a sort of different approach, and they ask the user to approve logins on their phone, right? So here's an example of Google's implementation on this. You try to sign into your Google account, and you get a little prompt on your phone saying, hey, are you this person that's trying to sign in, near Edinburgh? And then you just, you tap yes or no, and that's fine. The problem with this, though, is it's still vulnerable to phishing, right? Because if you live in a major city like London or Edinburgh, there are data centers near you, you could very well have a phishing website that tries to sign on to the service as the same time as you, using the credentials that you gave it. And when you get the notification, you go, yeah, I am trying to sign on to this service, unknowingly being phished, and you happily say yes, and everything's fine, probably, until all your details get stolen. YubiKeys, the sort of earlier ones, used an internal counter to generate codes in a similar fashion. They included the actual counter value in the generated code, so you didn't have these sync issues. But at the end of the day, all of these methods are still vulnerable to phishing. Just like the code card, with the token, with the YubiKey, with login validation, all of these methods are still vulnerable to real-time phishing, because the problem is that your code generator is working independently, so it's unable to validate the website's identity. Because it's not connected to your computer, it has no way of knowing that you're actually connected to the real domain name and that this is actually the real website that you want to speak with. So, as a sort of solution to this, there are challenge response protocols that use what you're trying to do with the service as part of the authentication system. So a few UK banks, namely Barclays, NatWest, and RBS, use the chip authentication program. They use it to verify transfers to new recipients, when you're doing something sensitive like changing your address or signing up for mobile banking. And basically the idea is you're given this handheld reader, or you have it built into your mobile app, and whenever you're doing something sensitive on the website, you're asked to confirm the changes that are being made independently on this handheld reader. So, for example, if I want to make a new payment to someone, I have to go and type in the account number and the payment amount into this token generator. So as a result, even if I'm being phished, it doesn't matter, because I still have to independently validate the account number and the payment amount. So unless I'm also being tricked into typing in the wrong account number, the wrong payment amount, then I can't have my money stolen. Yeah, seems there's an issue with the video. Okay, right. We're back.
Sorry.
So, because you have to confirm the account number and the payment amount that you're transferring to on an independent mechanism, even real-time phishing is sort of pointless here, because if you're being asked, enter this completely different account number from the one that you just entered, you'll probably be a bit suspicious of what's going on there. And the chip authentication program basically piggybacks the chip and pin process to generate an 8-digit code. So you use a regular bank card, and really there's a very, very small change to the way that bank card is set up. Basically, this is a look at a Barclays UK debit card, and you've got 3 applications installed on the debit card. And there's this additional Barclays application listed at the bottom that's used for the online banking system. And basically, after verifying the user's PIN, the Authenticator just asks the card to sign a fake purchase. So the Authenticator pretends that you went to Costa or something, and instead of buying a coffee for £2, you have all this additional transaction data that includes the account that you're transferring to, or perhaps that you're changing your address. This information that you want to validate. So obviously, because your bank is able to validate transactions as coming from your card as genuine, they're able to take this fake transaction and validate that it was signed by your real debit card, just using the same mechanism. And as I mentioned, because the user has to independently confirm the amount and the account number, phishing attacks are useless. So this works really well for banks. It massively cuts down phishing attacks. This works fine even if the user's PC has malware on it, again, because of that independent verification system. But this is something that's highly specific to a financial institution. If you're using this to just generally log in on Facebook, it would be really impractical to, have an independent device that you type in, hey, do you want to go to the cinema tonight? And then you get a code that you have to enter into Facebook Messenger. It just wouldn't work. It would be terrible user experience. So, if you sort of think of a more generic version of this approach, can we make a signature where we're tying that to the domain name, right? Because phishing attacks rely on the user noticing that the domain name that they're on isn't the domain name that corresponds to the real website. So as long as the domain name matches bar man in the middle attack, we're okay. So some organizations use smart cards with client authentication certificates to sort of get around this. The U.S. Department of Defense is probably the world's largest adopter of the system. They use it for their webmail and all of their web infrastructure. Spain has a similar nationalized system where you can sign into online banking using your Spanish national ID card. But the problem is that there's a limited number of identities that can be stored on this smart card. So, this is fine if I have a smart card issued to me, as again, using the example of the Department of Defense, and I want to sign on to the Department of Defense's website, right? So it's okay for me to have that one-to-one correlation with my identity. But, I don't necessarily want every website to have this, this single identifier of me that follows me around, right? Like, if I create an account on some random person's blog, I don't necessarily want them to know, my national ID number. I don't want them to know my full legal name. So, instead, there's this new standard called U2F that Google have been huge adopters on that tries to be a modern version of these client authentication certificates. And a lot of websites have started picking up on this standard. As I mentioned, Google are huge adopters of it. GitHub have also picked it up. Fastmail use it. Facebook use it. Dropbox use it. Duo use it. Basically, you have these little USB keys. They're newer UB keys. They work sort of in a similar way as the older UB keys work. But when you go to sign on to a website, you get this little prompt that says please insert your token into your computer and push the button on it, and it waits for the token button to be pushed, and then it uses the information that it gets from the token to authenticate you. And basically, in this case, the web browser acts as a middleman between the token and the web servers, right? Because the web browser is aware of which domain you're going to. It's aware of a bunch of attributes regarding the connection, so it can't be deceived like a human eye would be deceived. And U2F helps with the anonymity issue because a unique private key is generated on the device for each account on each service. So, because the key is based on the domain name, phishing attacks are impossible. If I use my U2F key on Facebook.com, it will generate, one key. But if I go to fakefacebook.com, it will generate an entirely different key, which is useless on the real Facebook.com. And here's a sort of, complicated algorithm of how that works. You've got all this information coming in from the server, which the browser passes along to the token. Token comes back with a signature, and then the server verifies that. But let's sort of break this down into pieces. Basically, the sort of core fundamental part of why this is secure is because the key generation process is fully handled by the token in hardware and can't be extracted. There's no way for you to, if I leave my U2F token out on a table, there's no way for you to take that and without physically destroying the token using an electron microscope, spending a lot of money to look at the silicon, there's no way for you to easily or really feasibly extract the private keys from the token. So first, the user registers their key with a service, right? So I go to Facebook and I say, okay, I want to protect my account, and I want to sign in using U2F from now on. And basically, when you do this, the server generates a challenge. So it's just this random string to make sure that the token that's being registered is a fresh registration. It's something that's happening right now. We're not stealing someone else's token. So the server takes that challenge, passes it along to the browser. The browser takes information about the current session. It takes the domain name. It takes the username on your service. And it takes that challenge and it passes it along to the U2F token. And your U2F token will start flashing and it will confirm, do you want to generate a key for the service? And so you push the button and it generates the key. You send it back over AJAX, you send back the form, whatever. And the server validates that it received, new public key. And it validates that the challenge that it previously generated, this long random string, was indeed signed with the public key that it received. And if everything checks out, then it can store that token identity. Now the service has a public key specific to this user on this service on file. So this is something, again, it's unique to the service. If I wanted to, I could use the same U2F token across 2 accounts on Facebook, and it'll get entirely different public keys, because again, there's that username field as part of generating the identity. So we're set. We're ready to use this token for future authentication. So in authenticating the user, we ask for another signature, but we give the token details about the identity that it previously generated. So the server looks up the token identity, it generates another challenge, this big random string, and it calls this sign function instead. So it passes that along to the token, the token generates a key, passes it along back to the server, and the server validates the challenge. And if the challenge that it passed along was signed by the same public key that it recorded during registration, then we know that the user is in possession of the private key that they provided at registration, and we know that everything's fine. The math checks out. But there's one sort of nitpicky problem about this, right? This helps with phishing, but it doesn't help for those nation-state attack scenarios where the adversary is able to present a valid certificate for a domain. So if I'm Google, right, and I'm someone who nation-states would like to attack, say, for example, China. China has a lot of certificate authorities that they can place political pressure on to create a valid certificate for google.com that will validate in a browser. So, you'll be connecting to google.com, you'll get, the green bar, everything will seem fine from your perspective. And the adversary can simply proxy your connection. All they need to do is just pass along the challenge, your browser signs it, your browser comes back with a signed challenge, they pass that along, and now they have a valid session for you, right? Because as far as the browser knows, you're talking with the real server. You're talking with the browser, the server has a certificate that it trusts, so it seems fine. But further, there's a proposed specification to TLS which tries to add a self-signed client certificate to the TLS handshake so that this proxy step doesn't work. And you can pin U2F identities to a channel ID. And here's a modified version of the U2F flow to include this channel ID process. Essentially what happens is your browser creates a public-private key pair, and it sends the public key of that pair along when it starts the TLS connection. Your man-in-the-middling server is going to have to create its own key pair, right? Because it doesn't have knowledge of the private key that you created, so it's unable to sign messages with that public key. It has to make its own. So you pass this information along to the server. The server, same as before, looks up the token identity, generates a challenge. The man in the middle, proxies that information over. However, as I mentioned previously, the browser has information on the whole session context. So it's aware of this session ID. So it includes that ID with, in the signature process. So in addition to the challenge, you also have this unique ID valid only for this session included with the signature. So the token, receives that, signs that, same as usual. And when the proxy passes that along, the server, looks at the signature and it goes, okay, this matches the challenge that I gave you earlier, but the channel ID that's in the signature doesn't match the channel ID for this connection. So as a result, the man-in-the-middling attack is useless. So you can own the entire stack in between the user and the server, and U2F will still protect you. at this point, the only way that you can break U2F is if you have malware on your machine that's actively compromising the signature process, so that it doesn't have to do the channel ID processor, so that it passes it along to the attacker. So although the only issue is that hardware U2F tokens are really difficult to use on smartphones. I mean, you could, take a newer smartphone with USB-C, or even a smartphone with with micro USB, and plug a U2F key into it. But the browsers don't really support it, and it's sort of awkward to have a token dangling out of your smartphone. So there are software implementations of the same thing, which you could use on a smartphone. When you generate a token, it includes information about the U2F device that generated the token. So, if you're a bank, you can say, no, I only want hardware tokens. If you're a blog, you can say, nah, I'm okay with software tokens. So, it is flexible enough to support, even the most paranoid of use cases, but also, sort of more lenient use case. But additionally, at the minute, U2F has very little support outside of Google Chrome. There is a Firefox bug that's open to add U2F support for Google Chrome, and Mozilla are hoping to add U2F support to Firefox by the end of second quarter this year. So overall, this is a pretty exciting technology. There's a lot, coming into place with it, and hopefully it'll help make the web a little bit safer. Well, thank you very much.
Thanks, Henri. So we've got about just over 10 minutes for questions, if anyone has them, or I can start off if no one has them. Okay, not being particularly technical myself, but as a member of the public, what would they be likely to use something like this?
So the question was, would a member of the public be likely to use something like this? And I think so. I mean, if you sign up for online banking and, you get a token in the post from your bank, and they say, when you sign on to online banking, you'll need to plug this in and push the button, and it'll validate your identity. I could see it catching on. It's not something that's cumbersome to use, and in fact, it's easier than the current solution of your bank sending you, an authenticator device, which you have to plug your debit card into, generate, code, type that in. So it could catch on, but it does have that sort of higher barrier to entry, in that you need to buy. Although inexpensive, these tokens tend to float around $10, but you still have to buy the hardware to use it.
And how do you know? So can anyone make these tokens, and how do you know you're not buying a dodgy one?
The organization behind the standard, FIDO, do have a certification process for the tokens to make sure that they're adequately safeguarding the private keys. But you can make your own. There are completely open source U2F tokens where you can buy the pieces, solder them together. So because it's an open standard, there is that sort of flexibility of building your own or using a commercial one. But again, the service provider can tell if you're using one that you made yourself or a commercial one, and decide whether they want to trust that or whether they want to use one from a company that they trust.
Okay. And hogging it just for one more second, this is a USB device, right?
Most U2F tokens are USB devices,
yeah.
But as I mentioned, you can have software ones, and there are also NFC U2F tokens as well.
I know from a PwC perspective, you can't put anything into USB port. I think
right.
USB might be on its way out. So, anyway, does anyone have any more interesting questions?
So how do you, based on keys, so is there any sort of key management involved?
Could you repeat the question?
Yeah. So the question was, is there any sort of key management involved with a U2F token? And there isn't. The token itself actually has no onboard storage. What it does is, when you go to create a signature, it algorithmically recreates the same private key based on a starting private key that it has burnt into its memory. So it's able to create unlimited identities as long as the service is able to provide it with that sort of ID from which it can then recreate the private key. So there's no way to reset a token, but you can just deregister the token and it'll create a new identity the next time you register it.
What happens if you lose the token?
So the question was, what happens if you lose the token? It's useless without your password.
I meant for like getting back into all your accounts, because obviously you need
Right.
the token to log in.
So that would then depend on the service in question, right? So if you lose your token and need to get back in, they'll need some sort of recovery method, and that's where again it sort of gets sticky, because there have been a lot of social engineering cases where people contact support and say, I've lost my token, can you get me back into my account? So then there is that need for, okay, what do you do for recovery? In my case, I have two tokens. I have one that I carry on me, and I have one that I keep in a locked box at my flat. So if I lose the token that I carry with me, I can use the one in my flat to sign on to my accounts, deregister the lost token, and then add a new one when I get one. Yep.
This sounds quite similar to what you come across Steve Gibson and Squirrel. Sounds like the same mechanism to take a domain and an identity and create a unique private key. Do you know if it's the same behind the scenes?
So the question was whether it was similar to Steve Gibson's solution to create identities based on the domain name. I wasn't aware that he was looking into that, but I'll look into it when I get the chance to. I don't know if it's related. As I mentioned, it is an open standard. It's something that's being done in the public. It's something that anyone can contribute to. So you very well may be involved in the process of working on the specification, but I'm not sure if the two projects are related.
Do we have any more questions?
Yeah, go ahead.
Yeah, so you say that the websites can check what kind of token is talking to us. What stops you from, say, make a token that pretends to be YubiKey? Is there any authentication?
Yeah. So the question was, is there any way to validate that the token is being faithful about its identity and not claiming to be, a commercial token when actually it's a homebrew one? Basically, what's happened is the manufacturer embeds a private key into the memory of the token. That's for each batch. So say like every 100,000 keys, and when you ask the token to validate its manufacturer, the token signs the message using this private key. So you give it a challenge, it signs the challenge with the information about itself using this private key, so you can't replay that information. In theory, if you extracted the private key from the token, you could do that. But again, these tokens are built to be resilient against private key extraction attacks, so it'd be really expensive and just generally counterproductive to try to do that.
Anything else? Going once, going twice. Okay, well, thank you very much,
Cool.
Henry.
Thank you.